All right, let's dive into the two biggest questions in all of chemistry. Seriously, these are the fundamental rules that decide everything, from why an egg cooks to why a star explodes. We're going to break down the rules that govern all change in the entire universe. Ready? So think about this for a second. An egg fries, but you've never seen one unfry itself, right? An ice cube in your drink melts, but it doesn't just decide to refreeze on its own. It seems like the universe has a one-way street for how things happen. So what's going on here? What invisible force is stopping the movie of our universe from just playing in reverse? Well, it turns out you can understand pretty much every chemical process in existence by asking just two super simple questions. First, will it happen at all? And second, okay, if it will happen, how fast is it going to go? The first question, that's the world of thermodynamics. And the second one, that's all about kinetics. Let's tackle them one by one. Okay, first up, thermodynamics. You can think of this as the universe's ultimate rulebook. It tells us if a process is even possible, if it can happen all by itself without any outside help. In chemistry, we call that spontaneity. An ice cube melting in a warm room, totally spontaneous. The other way around? Yeah, not so much. Now, the secret to understanding if something will happen on its own is this one huge concept called entropy. You've probably heard it described as a measure of disorder or randomness, and that's right. The second law of thermodynamics basically says that for any spontaneous change to happen, the total entropy, the total disorder of the universe has to go up. The universe just naturally drifts towards being messier and more spread out. The physicist Rudolf Clausius put it perfectly with this quote: "The total amount of energy in the universe is fixed. It never changes. But the total amount of disorder is always increasing. It's constantly pushing towards a maximum." That one idea is why your room gets messy on its own and why heat always flows from a hot coffee cup into the colder air around it. But hold on, it's not just about chaos winning out. There's another major force at play, and it's called enthalpy. The simple way to think about enthalpy is as the total heat or energy in something. And just like a ball naturally rolls downhill, systems in nature prefer to be in lower energy states. So to really know if something's going to happen, you have to balance this drive for lower energy against that other drive for more disorder. And the thing that balances them both is Gibbs Free Energy. This is the ultimate decider. It takes the energy part and the disorder part and mashes them together into one single value. And the rule is incredibly simple. If the change in Gibbs Free Energy is negative, the process will happen all on its own. It's basically a green light from the universe saying, go for it. And this table here really breaks it down. Look at that top row. If a reaction releases heat and gets more disordered, it's a slam dunk, always spontaneous. And the bottom row? If it costs energy and creates order, forget about it. It's never going to happen on its own. The two in the middle, though, that's where things get interesting. That's where temperature becomes the tiebreaker, deciding whether the drive for low energy or the drive for high disorder wins out. Okay, so this is amazing. We can actually predict whether or not something is possible. But what do we do with that knowledge? How do we take a spontaneous process, like burning gasoline, and turn it into something useful, like actually moving a car down the road? Well, the theoretical blueprint for doing this perfectly is called the Carnot Cycle. It's his ideal four-step process for a perfect heat engine. In a nutshell, it shows how you can take heat, use it to expand a gas and do work, then release some waste heat to get back to where you started, ready to go again. It's the gold standard that tells us the absolute maximum efficiency any engine can possibly have. So thermodynamics is incredibly powerful. It tells us what's possible, but it has one giant blind spot. For example, the laws of thermodynamics say that a diamond turning into graphite, pencil lead, is a perfectly spontaneous process. So why isn't your diamond ring turning into dust? This is where we hit a wall, because the word spontaneous says absolutely nothing about how fast. And that brings us to Act 2, and our second big question. To understand the how fast part, we have to jump into a whole different field, chemical kinetics. This is all about the rates of reactions, how quickly the possible actually becomes a reality. And the most important idea in kinetics is actually pretty simple. For any reaction to happen, the starting materials don't just magically turn into the final products. They first have to climb a hill, an energy hill. Even if the final destination is way down at the bottom, they still need an initial push to get up and over the top. The height of that energy hill has a name. It's called the activation energy. Think of it as the entry fee for the reaction. If the hill is really tall, a high activation energy, the reaction is going to be super slow. If the hill is just a little bump in the road, a low activation energy, the reaction will be lightning fast. So how can we make a reaction go faster? How do we get more molecules over that hill? Well, we can pack more of them into the same space so they bump into each other more often. We can make sure they hit each other in just the right way. But the real game changer is usually temperature. Cranking up the heat is a double whammy. The molecules move faster so they collide more often, and they hit each other with more energy, meaning more of them have enough juice to make it over the hill. And this whole relationship is summed up beautifully in the Arrhenius equation. Now, don't worry, you don't need to memorize the math. Just appreciate what this thing does. It's the elegant formula that mathematically connects the three things we've been talking about: the height of the hill, the temperature, and the actual speed of the reaction. It's kind of beautiful, really. So, we can speed things up by adding a bunch of heat. But what if there was a better way? A shortcut? What if instead of forcing molecules to climb over this giant energy mountain, we could just give them a tunnel straight through it? Well, that's the magic of catalysis. A catalyst is basically a chemical matchmaker. It's this amazing substance that dramatically speeds up a reaction, but it doesn't get used up in the process. It's still there at the end, totally unchanged. And how does it work? It gives the reaction a completely new path to take, an alternate route with a much, much lower activation energy hill. I mean, just look at this chart. The effect is crystal clear. The catalyst doesn't change where you start or where you finish at all. All it does is lower that massive energy barrier in the middle, creating a super fast shortcut that makes the whole journey from A to B ridiculously easy. Now, catalysts pretty much come in two main flavors. You have homogeneous ones, where everything's all mixed together in the same liquid or gas, and then you have heterogeneous ones, where the catalyst is in a different state, like the solid metals in your car's catalytic converter that clean up exhaust gases. These things are the backbone of massive industrial processes, like making fertilizer for the world's food supply. But you know, the most sophisticated, most efficient, and flat-out most incredible catalysts on the planet aren't in some giant factory. They're working away inside every single one of your cells, right this second. We call them enzymes. And enzymes work with this unbelievable precision, using something called the lock and key mechanism. It's exactly what it sounds like. Each enzyme has a perfectly shaped little pocket, that's the lock, and only one specific molecule, its substrate, the key, can fit inside. The key sides in, the enzyme does its chemical magic, and then it releases the new products, ready for the next key, sometimes millions of times per second. And just how fast are we talking? Look at this number, 10 to the 15th power. That's a quadrillion. The enzyme catalase, which your body uses to handle a toxic byproduct, speeds up a reaction by a factor of 10 quadrillion. A reaction that would normally take years to happen is over in a fraction of a second. It's just mind-boggling. So there you have it. Thermodynamics tells us if it'll happen. Kinetics tells us how fast. These two simple ideas govern literally everything. Every single breath you take, every bite of food you digest, is your body expertly navigating these energy hills and reaction speeds. It really makes you wonder, what other parts of our world are shaped not by what's simply possible, but by what's just fast enough to matter?